So let's start off. Let's continue. Why did I say let's continue actually and not really start off? Very
Yes, sir.
simply, we're going to be continuing on with something which you have learned in a previous chapter earlier, namely something from stoichiometry and how reactions work. So, for instance, let me directly look at what is going to be a solution over here. When you're going to be considering a solution is going to be something where you're going to be having, what to say, only one phase visible here, the liquid phase. And simultaneously, in this particular phase here, you're going to be having mixtures being possible. So mixtures in this are basically going to be mixtures in solution phase, in liquid phase, are basically what come out of the category of solutions predominantly. Now, when it comes to solutions over here, let's start off with understanding what are the variables which we need to start learning about so that we can keep track of, so that we can understand what is really happening. So you're studying this particular phase called the solution phase over here, which is mainly going to be a liquid phase, where you're going to be having the substances in mixture form in liquid phase over here. So when you're studying the solutions over here, you need to now look at mathematical variables, which are important to study here, which are basically properties or mathematical functions of solutions. What are these going to be? These are going to be your concentration
Concentration.
terms. So when it comes to the concentration terms here, all the concentration terms which are applicable for solutions come into this category here. You will have molarity, of course, as a starting. You will have molality. You will have normality. You will have mole fraction. You will also be having weight percentage. You will, of course, be having weight by volume percentage. You will also be having volume percentage. All your standard concentration terms apply over here, along with the weird ones also. When I say weird ones over here, you can have questions involving hydrogen peroxide. All right, you can have some questions involving them. In those questions for hydrogen peroxide, they might give you concentration from the point of view of volume strength. And then the rest of the question is going to be depending on the volume strength being converted into molarity and then solving. So if you don't know how to convert volume strength, you're straight away in trouble there.
Hmm.
Next up is going to be your, what to say, same analysis is applicable for sulfuric acid as well. Basically, oleum, percentage strength. They might play with that. They might give you that particular thing also. You'll have to convert the percentage strength meaningfully into whatever is going to be the concentration.
Hmm.
Now, so initially you're going to be having a quick recap of all of these concentration terms, which are going to be discussed over there in the chapter. Then we are going into more details. I'm just going to touch upon the overview of the chapter today right now. So next up is going to be how we are going to be having among these variables here. We learned about some of these variables now. These variables here, some of them are going to be useful for understanding some properties. Some of them are going to be useful for understanding other properties. For instance, when you talk about solutions over here, you've already learned about solutions a little bit in one other chapter before. Which chapter did you learn about solutions?
Ionic. Hmm.
Ionic. So ionic equilibrium was a chapter where you completely learned about solutions again over there. Right?
Hmm.
In that
Yeah.
chapter, which of these mathematical functions are important?
Mole fraction.
Mole fraction was important on ionic equilibrium, sincerely? You think and tell me? Only molarity, what the hell? Sincerely think and tell. Everything is concentration term, this concentration term, that correct?
Yeah,
Yes or
molarity.
no?
Yes. Yeah.
They're all molarity. There is no mole fraction there.
Not mole fraction. My good. I was thinking.
Hmm. So molarity is going to be the thing which is going to be constantly used over there.
Hmm.
Why is molarity more critical for ionic equilibrium? Because this is an equilibrium chapter. So equilibrium chapter is generally going to be having experimental data
Hmm.
measured at what condition usually?
Standard or room temperature.
What? Constant?
Yeah. Oh, pressure, concentration.
Constant temperature is the real thing which I'm looking for here. Pressure is not going to be the case.
Sir, not pressure would vary, no?
So why? Because equilibrium constant is a constant at a given temperature. So at a
Yeah.
constant temperature, you'll play around with it.
Okay.
Whereas now, when it comes to the next chapter of solutions here, which is going to be this new chapter here, where you're going to be learning more about solutions completely over here. This is going to be involving, what to say, understanding thermal properties of solutions. Think of this
So
chapter.
temperature is not constant.
So what does thermal basically mean?
Temperature is not constant, basically.
Yes. Thermal connections with solutions. So when you want to understand the thermal connection with solutions here, what do you now do here? You basically go into the next aspect over here, which is basically directly going to be the next set of mathematical functions which you're going to be doing. So here you're going to be varying temperature absolutely. So if we are varying temperature truly over here, then which property will be maintained a constant? Which concentration term is useful now?
Molarity. I
Huh?
mean, volume would,
Molarity is what type? It is moles per liter.
yeah.
Liter is
Molality.
volume of solution.
Molarity, yes. Yeah.
Right. So it deals with volume of solution. So if it deals with volume of solution here, then there is a problem now. Correct? What is the problem if it deals with volume of solution? Can you tell me? Have you tried heating a liquid?
Tried what, sir?
Have you tried heating a liquid?
Yeah, volume. I mean, it's gonna expand now. It'll.
That's correct. So volume changes.
Yes, sir. Yeah.
The volume is changing when you heat the liquid over here. What does that basically tell you? It
That
tells
means
you
it
polarity changes with change in temperature.
molarity will also. Yes.
Right. That means molarity is useless.
Yeah.
Right. So molarity is not that useful here. Molarity becomes useful. I mean useless. So which one is going to be useful now?
Molality.
Molality.
Yeah. Not non-volume dependent.
So
Most
this
actually.
becomes more useful now, and this becomes more useful now in this chapter. So you'll be having in this particular case here, the concentration terms that are useful are now going to be mole fraction and molality.
Whichever doesn't depend on volume.
Correct. Whichever is not going to be dependent on volume, they will become more efficient here. Of course, when those two become more important, weight percentage, weight by volume percentage also start becoming more important. Meaning, in some questions, they might give you weight by volume percentage or weight percentage, and then you'll have to do some conversions and then arrive at what you have to do. Starting point of the question. So this is basically the initial introduction to what you're going to be needing as a prerequisite to start off with the solutions chapter. All right. So what you're going to be learning in solutions, as I mentioned, is what happens to different types of solutions. First, we analyze each solution in detail, and then we discuss what happens to different types of solutions at different conditions, thermally speaking, when we are changing temperature. So to understand it, you need to first understand some basics of a solution. So let's say we're going to be having some water. All right, in a particular beaker. You need to understand vapor pressure. I think you already know vapor pressure, na?
Yes, sir. Yeah.
So vapor pressure is basically going to be nothing but if I'm going to be having some liquid, like say water, present in a container.
Keep it.
So if I have water present in a container here, in this container over here, when water is taken, what happens is you're going to be having, if I put a lid on top of this container here like this, if I put a lid on top of it, what happens is you're going to be having water molecules basically, which are going to be present on the liquid here, like normal. Under normal circumstances, what happens is water molecules are present on the surface here will escape into vapor phase. Right, they will escape into vapor phase. What is this process by which they escape into vapor phase? that is going to be evaporation.
Evaporation.
So you're going to be having regular evaporation happening here, which will allow the water molecules of the surface to escape into vapor phase. So in this chapter, you'll be understanding a little bit more about exactly what's happening there during the process of evaporation. And when they evaporate off, what happens over here is they end up getting accumulated in the air over here. When they get accumulated on the surface or in the region above the surface of the liquid here, what happens is they get collected up on top of the liquid over here. When they get collected up on top of the liquid, these gas molecules or these water vapor molecules now start exerting a pressure on top of the liquid surface. That pressure that they exert is basically what is going to be called as vapor pressure. So vapor pressure is effectively going to be when you have a lid only, you have vapor pressure applicable. Because if you're going to be having it in the open, what happens then? Atmosphere is outside. Outside air will basically be there. What will it do? It will push all of these water vapor molecules away.
Yeah.
As simple as that. So you're going to be having, in this particular case here, evaporation is going to be happening, which leads up to vapor being collected. That vapor then exerts a pressure called as vapor pressure.
Yes.
Now, what happens over here is you will end up having this process as you end up having more and more vapor molecules getting collected.
Pressure. Makes sense.
As more vapor gets collected, condensation, which is going to be the reverse of this process. Condensation, which is going to be the reverse of this process, also ends up increasing in the speed in which it is going to be happening. Eventually, we will have a particular point at which the evaporation and the condensation will both reach a nice, happy equilibrium. All right, they will both reach a nice, comfortable equilibrium. In which case, your equilibrium, which is going to be established, is going to be H2O liquid
Equilibrium
with H2O gas. This equilibrium is going to be having an equilibrium constant Kp.
Vapor pressure.
That is going to be your vapor pressure. This means vapor pressure for water or any liquid at a given temperature is a constant. Equilibrium constant, right? It's an equilibrium constant.
Yes.
Vapor pressure is an equilibrium constant.
Sir, how can we guarantee that it's same for all liquids?
No, it is not same for all liquids. Right? The property is available for all liquids.
I mean, this is like
have their own vapor pressures.
Sir, I mean to say like, how can we say that for all liquids that the Kp will be P?
What are the variables which you assumed over here? You think at that? What did we assume? We assumed evaporation happens. We assume condensation happens. Correct?
That's it.
That's all we assume. Right? We assume anything else. So what's the problem then? Right?
Okay. Yes.
The idea is very simple, Ram. Whenever you're coming across something where you have to test if a logic applies in other cases, you have to check what were the assumptions you made on that logic. If the assumptions you made were preposterous, involved something else, then yes, it will not apply. Here, though, this is going to be perfectly applicable. Because the only assumptions we made were evaporation happens, condensation happens. Perfectly fair assumptions, right? No problems with making those assumptions. Okay. Now, next up. So in this particular case here, vapor pressure is an equilibrium constant. What does that mean? That means it is a constant for a given liquid at a given temperature. Clear?
Yes, sir. Yeah.
Oh, now, next up, we are going to be diving into what is going to be the next part of this entire thing, which is going to be, now you have understood that there are some more properties which are very important for liquids and solutions. First property being vapor pressure. Not just first, this is the only property. This is the main thermal property which is going to be connecting with everything else. Vapor pressure is going to be the main thermal property we are going to be studying now, and how vapor pressure changes. Good wind. I'm feeling nothing. Yeah. Okay. Next up. So now we have studied a little bit about vapor pressure. Now let's try to understand a little bit more about vapor pressure and a little bit more about solutions. So when it comes to solutions, now first things first, let's go back to the original definition. I talked about how liquid phase is what we are studying, and that we should technically, hopefully, have only one liquid phase. Meaning, we are looking at solutions which are like proper homogeneous mixtures, mainly, not heterogeneous stuff. Like oil and water is not what we are examining right now.
Makes sense.
So let's try to study a little bit more about homogeneous solutions over here. So when we talk about these homogeneous solutions over here, how can we break them down into different types?
Homogeneous.
So homogeneous solutions, correct? Let's break them down into types now. First off, what's going to be happening? What are we having here first? Gas plus liquid.
Yeah.
Correct?
Yeah.
So gas plus liquid left, what is going to be the case there? Most important property is going to be, of course, solubility of the gas. Right? Because how is it that the gas is dissolving? And what is going to be happening here? Solubility of gas is going to be critical over there. This solubility of the gas is going to be studied by a law called Henry's law. Now, when you're going to be considering solubility of gases in liquids, the idea is very simple. We only look at it from the point of view of if I'm going to be having a gas in a liquid. Usually we take water. Water is our main liquid. We're not going to be changing anything from water there. So the idea here is there are two types of gases now when you're dissolving gas in liquid. First one is, of course, going to be the type which is going to be directly dissolving but not reacting with the liquid. So it's just dissolving but not reacting. That is going to be one category. Second category, three categories, maybe not two categories, three categories. Second category is going to be those which react with water, like say HCl gas. Consider HCl gas. The solubility of HCl gas will be extraordinarily high in water. Correct? Why? Because if it dissolves in water and reacts with water, as what?
Then forward direction.
Yes, acid. It reacts as an acid, correct? So this will basically dissolve in water to give you HCl aqueous, which will basically not stop. It will break into
H plus Cl minus.
Correct.
Sir, what is the exact definition of homogeneous solution?
Homogeneous solution, now you're going to be having only one phase being clearly seen. And it is going to be something which is also going to be properly, fully, evenly mixed.
So how is gas liquid?
Yes.
So gas plus liquid is only a homogeneous solution if the gas mixes with the
Yes, the gas dissolves in the liquid.
If only, yeah. Okay.
Gases dissolve now. How do gases dissolve in liquid? You tell me. They will dissolve evenly only, na?
Dissolve what?
How will a gas dissolve in a liquid? You think it will? You have to push the gas in.
Push the gas. Yeah.
Literally.
Yeah.
So if it reacts, it reacts. If it doesn't react, it just occupies the spaces in between, literally, as you have learned in small classes.
Yeah.
More or less. So that's basically what happens over here. And it occupies those spaces evenly, relatively. Because gas moves around completely inside. It has good mobility, na?
Yeah, okay.
So now, when it comes to this particular case here, one category is going to be the category which doesn't react with the liquid. Another category is, of course, going to be the category which will react with the liquid. The category which reacts with the liquid, its solubility is incredibly high because it's going to be reacting and it will keep going in forward direction, solubility wise. Whereas the category which does not react, that we can study using Henry's law. So when you talk about this Henry's law here, it talks about how solubility of a gas.
So you said there are three types, right?
Yes, the second category is going to be, of course, the one in between over here. Something which dissolves something which is not going to be, something which reacts partially. So if it's reacting only partially, then what will happen? If you can force the reaction in the forward direction in some way, solubility will increase.
Okay.
Right? There are three categories in the sense. First is going to be doesn't react at all. Second is going to be the one in between. Third is going to be the one which reacts properly, like HCl.
Hmm.
So the in between one is going to be like a carbon dioxide type of shit.
Okay.
If I want to increase the solubility of carbon dioxide gas in water, how do I increase its solubility? I make the medium basic. Correct. Carbon dioxide gas, correct?
Yes.
So if I make the medium basic, what will happen? That will force the acidic reaction in forward direction.
Yes. Yeah, I know it is obvious.
Right. So
Yes.
you have to start playing the game according to the equilibrium there.
Okay, that's nice. Okay. Hmm.
You understand the idea here?
Yes. Yeah.
There seems to be fantastic rain. You might get your wish of the class ending on time by hook or by crook today. Okay. So solubility of a gas which is not going to be reacting at all. First category. That's what we are going to be studying using Henry's law. So in that case, the solubility of a gas depends on two factors there: temperature and partial pressure of gas above liquid. Basically, if you are going to be pushing the gas more forcibly into the liquid, more will dissolve. That basically means partial pressure of the gas above the liquid, if it is higher, more will dissolve. Quite obviously.
Yeah.
Right, literally. And temperature wise, what is going to be the case there? Higher the temperature, lesser the solubility. Very simply put, gas molecules have more energy.
More. Exactly.
You're going to be increasing temperature by more, correct?
So harder to react.
So harder to basically push them inside.
Okay.
All right. So you're going to be having solubility of a gas being something like this. So temperature, lower temperature, higher solubility. And partial pressure of gas above liquid, higher partial pressure implies higher solubility. So you learn this mathematically in a separate thing called Henry's law. That I'm not going to be going into. We'll look at that when you look at it.